Scholarly efforts to tell what light is began from the time of ancient civilizations, with notable, but in hindsight laughable speculations, followed by empirically grounded insights, paving the way to modern scientific inquiry. Ideas proposed by Isaac Newton, Thomas Young, and Albert Einstein propelled our understanding, but also revealed light in an ever more mysterious light. You've probably heard that light consists of particles, known as photons, perhaps if you've studied the photoelectric effect. But light also has a wave-like character, making it seem two-faced and pretty weird. It's often said that no one really knows what a photon is. You can think of a photon as a localized wave packet, as a compromise between particle and wave character. We have to accept that light obeys wave-particle duality, meaning that it's both a particle and a wave at the same time. Confused? You should be. Frankly, I've had enough of hearing such nonsense. This intellectual dishonesty is the motivation behind this video. If light fascinates you, then you deserve a serious explanation about what light is. The aims of this video are twofold. The first is to tell you what a photon is, by explaining the basics of quantum optics. Why delay? According to the late Steven Weinberg, one of the giants of modern physics, a photon is an elementary excitation of the quantized electromagnetic field. This statement isn't as scary as it might seem. I'll gently explain all the concepts in it so that you'll grasp its meaning. To fully understand this statement, a deeper dive into quantum field theory is needed, and you can find resources in the description if interested. The second aim of this video is to convince you that photons aren't particles. This may sound heretical, but remember, chances are that what you've heard about photons has been oversimplified and inaccurate. To convince you, I'll focus on just one argument involving metal plates close to each other in a vacuum. Amazingly, while this looks innocuous, quantum optics is the thread connecting it to seemingly distant mysteries. We'll get to all of this by the end of the video. You'll see bits of maths throughout, mostly just letters and symbols. If maths isn't your thing, relax. You don't need to understand it to grasp the concepts, which I'll explain gently from the ground up. Intriguing clues that electric and magnetic phenomena are intertwined emerged early in the 19th century, with seminal discoveries by the likes of Michael Faraday. For instance, Faraday showed that moving a magnet towards a coil of wire induces an electric current in the coil. The genius of James Clerk Maxwell condensed such phenomena into an elegant set of 4 equations, Maxwell's equations, truly one of the pinnacles of classical pre-quantum physics. If you have no idea what any of this means, that's fine. The key here are the letters E and B, representing electric and magnetic fields. More about fields later. For now, just appreciate that E and B represent the electric and magnetic aspects of nature. Since 2 of Maxwell's equations involve both electric and magnetic fields, electric and magnetic phenomena are deeply intertwined. We can't understand either in isolation. Maxwell's equations thus unified electricity and magnetism into electromagnetism. What does light have to do with all of this? Well, it turns out, quite a lot. Incredibly, Maxwell's equations imply that light is an electromagnetic wave, a wave of oscillating electric and magnetic fields. Let's understand this by looking at a familiar example of a wave. A wave on a string is a disturbance that travels along the string. Pick any one of the green particles or beads on the string and focus on it. See how it oscillates up and down? Let's now look at an electromagnetic wave. Focus on the red arrow, which alternately points up and down. It depicts the oscillating electric field at some position, as an electromagnetic wave passes by. Electric fields exert forces on charged particles, so if a charged particle were at this position, it would experience a force alternating up and down. It's a similar story for the magnetic field, depicted by the blue arrow, except that magnetic and electric forces act differently on charged particles. Please note, due to laziness, I'm going to say the letters EM instead of the word electromagnetic from now on. In summary, Maxwell revealed that light is an EM wave or field traveling through space, thus illuminating our understanding by unifying it with electricity and magnetism. A few years after modern quantum theory emerged in the mid-1920s, focus shifted to developing a quantum theory of the EM field. Paul Dirac, who won a Nobel Prize for predicting antimatter, made seminal contributions to this effort. Constructing a quantum theory is known as quantizing, and quantizing the EM field isn't straightforward. So, we'll look at just two essential concepts of the quantized EM field. These are: the electric and magnetic fields are quantum observables. They don't have definite values due to quantum uncertainty or fluctuations, but we can talk about their averages. Second, the state or nature of light, or the EM field, remember they're the same thing, is described by a quantum state. Let's delve into these two concepts further. The E and B fields of the classical EM field are classical physical observables. When measured, they have definite values. For example, a compass measures the direction of the B field at different points around a bar magnet. Better still, a magnetometer measures the strength of the field along with its direction. If we repeated this experiment identically, using the same bar magnet and making the same measurements, in principle, we'd record identical data from one experiment to the next. That's kinda obvious, you might say. Well, perhaps, except things aren't so simple when it comes to measuring the quantized EM field. In quantum physics, measurable things, physical observables, are more abstract than in classical physics. We distinguish quantum observables from their classical counterparts by hats on top of the symbols. Upon repeating an experiment identically, the measured fields will generally vary from repeat to repeat. But this variation isn't due to experimental errors. Magically remove all sources of error and the variation would persist. These fluctuations are intrinsic to the quantum character of light and are known as quantum uncertainties. We say that quantum observables don't have definite values, except in special cases. In passing, Einstein and Niels Bohr had famous debates, where Einstein expressed his discontent with quantum uncertainty, and Bohr offered robust rebuttals. To measure quantum EM fields, we require balanced homodyne detection. And while the fields may not have definite values, it's possible to calculate their averages and other statistical quantities. These reveal intriguing aspects of quantum light, and depend on the nature or state of light, which brings us to the second essential concept we have to look at. We saw earlier that classical light is a predictable oscillation of E and B fields. The fields have definite values. But since quantum EM fields don't have definite values, unsurprisingly, classical wave models can't capture light's quantum nature. We need quantum states to describe different states or types of light. These can't be pictured simply, as they are abstract mathematical objects, and we won't get into the maths. Many different classes of quantum states exist, each with properties specific to the types of light that they describe. You might think that different types of light refers to, say, blue versus red light, but it doesn't. It refers to more fundamental differences between classes of light. Don't worry about the details here. The various classes have distinct averages of quantum observables. What's meant by elementary excitations? Consider the vibrations of a string held taut at its ends, such as a bass guitar string. The vibrations may look complicated, but remarkably, we can break down and analyze this complexity in terms of more basic or elementary vibrations. It's kind of like building up a complex dish from its basic ingredients. Let's add a big quantity of this vibration, a smaller amount of this, and yet smaller amounts of other vibrations to build the overall vibration. These elementary vibrations, also known as harmonics, are the basic ways or modes by which the string can be disturbed or excited. By analogy, let's ask, What's the most basic disturbance of the quantized EM field, or equivalently, what's the most elementary excited quantum state of light? The answer is a photon. Remember this? A photon is represented by the quantum state shown. It's known as a quantum of the EM field. Things to note. The photon is fundamentally quantum in nature. It's not a wave. The elementary vibrations of a string are an analogy. It's not a particle. More on this later. And it isn't some weird combination of wave and particle. Remember, the abstract mathematical nature of quantum states prevents simple visualization. Depicting photons as localized wave packets is misleading and only perpetuates confusion. Quick point, there are different varieties of photons. Photons of red light, yellow light, and so on. To distinguish them, we could write informally the states shown. From now on, we'll focus on a single variety or mode, blue, yellow, or whatever you like, and just write the state 1 for a photon. What about more highly excited states of light? States with more energy? Simple. These are multi-photon states, known as quanta of the EM field. If a single photon state costs energy E, a 2-photon state costs energy 2E, a 3-photon state costs energy 3E, and so on. These energies differ by discrete chunks of E, which often leads to the incorrect conclusion that photons must be particles. Find out more about this fallacy in the references in the description. Can the EM field have no photons? A state of complete darkness, informally speaking? Yes. Unsurprisingly, we call this state the vacuum state, and we'll see later that it's pretty interesting. While photons are basic disturbances or elementary excitations, basic and elementary don't imply common or everyday. Remember, photons are inherently non-classical or quantum in nature. They're as far away from classical light as you can get, which is rarely stressed. The non-classicality of photons makes their generation challenging, although light sources which reliably emit photons on demand are in development. For instance, nitrogen vacancy centers in diamond are just one promising route to this goal. Photons on demand will enable emerging technologies, such as quantum communication and computation. If photons aren't everyday quantum states of light, do there exist states which are present in daily life? Absolutely. Lasers, used for partying, scanning barcodes, eye surgery, and much else, emit a special quantum state, a coherent state. Coherent states are almost like classical light, and thus far away in character from photons. They're a fundamentally different class of quantum states. A coherent state is a combination, or quantum superposition, of all possible photon states, including the vacuum state. This implies uncertainty in the number of photons. There isn't a definite value for the photon number. If the maths here looks a bit scary, you can relax now. This is as bad as it gets. Finally, we can now discuss why photons aren't particles by examining a beautiful and shocking demonstration of the quantumness of light. This ties together many concepts we've seen and illuminates the profound implications of the quantum EM field. Remember the vacuum state, the state with no photons, and supposedly a state of complete darkness? If photons are particles, the absence of any photons ought to be boring. Just like a still or undisturbed string is boring. Let's test this out by examining the averages of the EM fields. For the vacuum state, what are these averages? The angled brackets around E and B represent the averages of E and B. They're equal to 0. This makes sense. If there are no excitations or photons, why would the fields be non-zero? So, we conclude that in the vacuum, the fields vanish, right? Not so quick. We have to be careful. Take an everyday example. Imagine that during a week, the average temperature outside at midnight was 0 degrees Celsius. Was the daily measured temperature definitively 0? Probably not. The temperature likely fluctuated around 0, some days above 0, some days below it, and perhaps some days at 0. In the language of statistics, the temperature has a finite variance. This is revealed by squaring the temperatures and calculating the average of the squares, which would be non-zero. Now, remember that the electric and magnetic fields are quantum observables? Recall that they're uncertain and don't have definite values. Measuring the fields repeatedly in identical experiments generally yields different values. So, even if the predicted averages of the fields are 0 for the vacuum, could the fields fluctuate about 0? As for midnight temperatures, calculating the variance, the averages of the square of the fields, holds the answer. The calculation returns a non-zero variance. Wow, let's take stock of the significance of this. Quantum optics, the quantum field theory of light, predicts that when the EM field is in the vacuum state, the field averages are 0, but their variance is not. It's as though the fields can never be perfectly still or at rest. There's always some minimal activity, and therefore energy, present in the EM field, even in the absence of photons. Going back to the string analogy, imagine a string which is never at rest, but which always has slight ripples. This minimal fluctuation, or uncertainty, is a consequence of Heisenberg's uncertainty principle, which you may have heard of. If not, that's fine. The minimal energy is known as the zero-point energy of the vacuum. Want to insist that photons are particles? Okay, please explain the vacuum fluctuations and zero-point energy. How is it that even with no photons, the vacuum has this restless, dynamic character? Echoing Weinberg's description of a photon, Michael Redhead put a nail in the photons are particles coffin by writing the following. QFT stands for quantum field theory. Pause the video to have a read over this. As Redhead mentions, there's evidence for vacuum fluctuations and the zero-point energy. In 1948, Hendrik Casimir published an influential and foundational paper in which he considered two uncharged parallel metal plates placed very close to each other in a vacuum. He realized that the zero-point energy of the EM vacuum depends on the distance between the plates, d. Reducing d lowers the zero-point energy of the vacuum. Whenever energy depends on distance, we have a force, with the force acting to reduce the energy. Casimir thus concluded, astonishingly, that there should be an attractive force between the plates. This phenomenon is known as the Casimir force or the Casimir effect. Remember, the plates are uncharged, unlike charged capacitor plates that experience electrostatic attraction. In contrast, the Casimir force arises due to quantum fluctuations of the EM vacuum. Casimir predicted that the force or pressure varies inversely with plate separation, d, to the fourth power. This fourth power makes the force exceptionally small and impossible to measure other than at the micro or nanoscale. The effect was first measured in 1997, with the data agreeing well with theoretical predictions. Its experimental verification opens up problems and opportunities in nanotechnology. Have you ever wondered how some animals, such as geckos, defy gravity and stick to walls and ceilings? The feet of geckos have many microscopic hairs, and there's evidence that an attractive force, known as the van der Waals force, between these hairs and surfaces enables geckos to stick with such ease. But what's the origin of the van der Waals force? We now understand that vacuum fluctuations give rise to this force, Absolutely incredible. Again, this beautifully illustrates the profound implications of the vacuum EM field. Evolution, the tinkerer, may have handed some organisms a survival advantage by putting vacuum fluctuations to good use. Quantum optics has sharpened our understanding of light and the vacuum, concepts which have been pondered since antiquity, and has clarified the nature of photons. And, as is often the case in science, this is having ramifications for fundamental research and technological progress. Let's return to the earlier question of whether there's a state of complete darkness for the EM field. Given what we now know about the vacuum, the answer is no. There's always some light. Perhaps, then, we can take inspiration from this thought and allow it to illuminate our lives.